This is a demonstration of the traffic state and parameter estimation. Let us first consider an isolated movement. Recall the aggregated time-space diagram. For each trajectory, the arrival time is calculated by determining at what point the vehicle would have cleared the intersection if there was no queue or red light. The departure time is the time when the vehicle actually clears the intersection. The control delay is defined as the difference between these 2 points. In this example, the vehicle stops only one time. The arrival and departure histograms are plotted for all observed trajectories. In this example, the cycle length is 90 seconds. The green split is shaded green, the arrivals are shaded red, and the departures are shaded blue. It is important to note that the trajectories are aggregated according to their arrival time within their respective cycle. Therefore, all the arrivals are within the first cycle, and some of the departures extend to the following cycle if the vehicle fails to pass the intersection within the cycle in which they arrive. From the aggregated time-space diagram, we get the arrival and departure histograms. With a given penetration rate, the total number of arrivals and departures of each time step can be converted to an arrival/departure probability. This probability is scaled by dividing the number of arrivals or departures by the product of the total number of cycles within the aggregation period and the penetration rate. The arrival probability curve is used as the input for the traffic flow model, and the dashed blue line is the output departure profile. The traffic flow model can also provide the estimated average delay. The legend compares this estimation with the measurements from the observed vehicle trajectory data. The actual penetration rate can be estimated by matching the average delay from the model with the real-world measurement. In the bottom right figure, the red dashed line indicates the model's current penetration rate, while the blue curve represents the difference between the model and the observed average delay for different penetration rates. Here, we show different prediction profile curves for different penetration rates. As the penetration rate goes up, the estimated arrival probability goes down. In addition, the estimated average delay decreases. If we set the model at the optimal penetration rate, not only is the average delay consistent between the model estimation and observed measurements, but the departure profile prediction closely matches the observed departure curve. When we underestimate the penetration rate, the model estimated average delay is larger than the observation. When we overestimate the penetration rate, the model estimated average delay is less than the observation. Next, we can see how the probabilistic time-space diagram can reconstruct the aggregated time-space diagram from before. The probabilistic time-space diagram gives the probability of a vehicle traveling in the spatial-temporal space, where the more darkly shaded areas represent higher probabilities. Finally, we can predict how the time-space diagram will shift for different signal parameter changes. We can change the offset between intersections to adjust coordination, or we can adjust the green duration of this movement. As the green duration increases, the trajectories can pass to the intersection with less delay. We now extend the model to a general network. This is the isolated movement case from before. We now consider a coordinated movement case. While the isolated movement has only external demand, the coordinated movement has both external and internal or coordinated demand. Here we will show how the internal arrival can be predicted from the upstream movement departures. Consider the scenario where both intersections share the same cycle length c. Let us call the upstream movement movement 1, and the downstream movement movement 2. The turning ratio captures the share of vehicles from movement 1 that will advance to movement 2. We also record the free flow travel time and relative offset between both intersections. The blue histogram illustrates the upstream departures from movement 1, while the red histogram illustrates the downstream coordinate arrivals to movement 2 from movement 1. The dashed red line represents the downstream arrival predictions. The downstream arrival is predicted according to the following equations, which incorporate the relative offset and the turning ratio. Delta t reflects the offset between the two movements. Since these curves are calculated through trajectory aggregation across many cycles, delta t is confined to one cycle. The reduction in the number of trajectories between the upstream departure from movement 1 and the downstream arrivals occurs because of the turning ratio. In conclusion, the downstream arrival can be estimated by a simple transformation of the upstream departures. As a final point, we illustrate the general framework for queuing model calibration for a corridor. We start with the aggregated time-space diagram of the corridor. After calibration, we generate the probabilistic time-space diagram, which indicates the probability of a vehicle being in a certain queue position at a certain time. The aggregated and probabilistic time-space diagrams can also be converted to space mean speed heat maps. Note that the observed and model estimated space mean speed heat maps have similar patterns and queue profiles.